going to open up sort of a very simple, like, little loading case so you sort of can see like how you could start building a simple structure. And if you want to follow along in terms of doing this, please, if you go to coursework, you'll actually find a simple structure. It looks like this, and let's go ahead and take a look at it. I'll kind of flip it over to the bottom, and we'll just sort of think about how we apply loads to this, and ultimately how we do the analysis on it, just understanding it. Now, what I'm going to do is, and I'll recommend this for any sort of time you start working with a new analysis tool, is just start with something simpler. Don't start with your fantastic building, which has 16 stories and some very exotic structural system. Always start with some simple little load case that is predictable and that you can control to really understand, are you really using the tool and getting the results you expect, or is the tool using you and you're just getting sort of pretty pictures that really you have no idea what they mean. So always go ahead and start with some simple little load case. So even this one's kind of complicated. I might be better to start with just 4 columns and the beams in there, but test it using something really, really simple to get started with, because I think even with the energy analysis tools, you'll have, it's that same thing. If you start with something really, really complicated, you really have no idea whether it's giving you accurate results or not. It's just giving you a lot of numbers. And don't mistake a lot of numbers for being precise or accurate. It's just kind of a lot of information. So always start with something relatively simple. So don't start with your own buildings. Try it with something simple. So if you want to download this and get going, just out there on coursework, you will find, the session 11 starting point. I have it in a couple of different places. I have something where I've applied some boundary conditions and where I've applied the loads. So in terms of working with that, you can start with any of those. I'm going to start with the first one and apply the boundary conditions, just because you may need to do this to your model if you started with an architectural model just to get ready for analysis. We have to put some things in place. So what we need to start with is, we've got these structural elements. I got some beams, I got some floors. It's kind of doing pretty good. 2 basic things we need to do. One is boundary conditions. Let's talk about that. Boundary conditions is this whole notion that really those columns are going to rest on something. And in order to have the building not move in space, we have to sort of say something about how it's grounded. And we could sort of choose different ways that it could be grounded. It could be grounded with fixed connections or pinned connections, or moment-resisting connections. There's all these different sort of connections we might apply there. And it's actually quite important, because the type of connection you assume will say a lot about really how the stresses are resisted by the building. So let's go off, and it's all going to start by going over to the Analyze tab. And we're going to this part that says Boundary Conditions. And what I want to do is put a boundary condition under each of these different columns. Now, I'm looking at the full system here, and just because I like to go through and actually sometimes look at it a little more simply in terms of understanding it, what I'm actually going to do is duplicate this view. And I'm going to basically call this the analysis model. And what am I going to do? I'm just going to isolate only the analysis model, because that's actually a little bit simpler. And if you're used to working with something like ETABS, that's probably what you're used to seeing. So what I'm going to do is go to Visibility Graphics. I'm going to turn off the model categories, but leave the analytical model on. Okay, and it'll look more like that. So kind of a simple plane, simple columns, beams, stuff like that. Yeah, sometimes it's a little bit easier to work with. So I turned on the analysis model. If you don't see that, another thing you may need to do is there's a choice down here about turning it on or turning it off. Because if you turn it on, again, it takes a little time to calculate it and keep it updated in the model. So at some level, that's looking awful like what a lot of you work with in ETABS or other sort of systems. You go through and you put some nodes in, you put the basic members in there, and then we're going to start applying loads to it. So the boundary conditions in Revit works like this. Under the Analyze tab, you have this choice for boundary conditions. And if I choose boundary conditions, the first thing it says is, oh, you can't put boundary conditions in here. You don't have any boundary conditions loaded. And all that's going on here is, if you had started with the structural template, they would have been loaded. Since we started with the architectural template, they aren't loaded yet. That's okay, we can pull them on in and we'll be back to where we need to be. So it just says, by default, in architectural things, I don't load them. You better go load some boundary conditions for me. So, no worries. We'll say, we can do that. We're going to go to the Insert tab and load a family. Turns out there's boundary conditions families. Who knew? And you can choose those for fixed, pinned, roller, and a variable condition. That's something where you can control, you know, do you want a little X, do you want a little Y, do you want some moment? You can kind of just choose of all the different things, which things you want to say you're resisting. So I'm going to load them in. So they're all in there. Nothing looks like it changed very much. But when I go back to boundary conditions, it still complains because after you load them in there, you still have to sort of map them to what it thinks of as a fixed or a pinned condition. So check this out. See that little arrow hanging out right there, that teeny tiny little arrow? Like Rooms and Areas has one of those little arrows and no one ever finds them again. There's this little arrow that brings down a sub-menu or a little dialogue, which will then let you go through and say, my fixed condition would map to the fixed condition. Pinned, roller to roller, and my user defined is to variable. So you just have to do some mapping because, you know, I might give you a boundary condition and you might load it into your project and use it. You know, it's part of something that your firm came up with, but you can do some matching in there. These are actually all the structural settings in terms of how they look on the screen, what sort of load cases. There's some standard load cases that all look pretty familiar to you if you're from the structural analysis side of the house in terms of dead loads, lead loads, lag loads, wind loads, snow loads, things like that. There are also load combinations, and I think by default there are not any load combinations defined. Almost all of the structural analysis tools have their own load combinations built into them. So you can say, you know, what is it? Is it 1.6 times the live load plus 1.2 times the dead load? Okay. Yeah, or you know the 8 other cases you're supposed to be considering also. You know, so you can define all those different load cases. But the truth is, you don't tend to need to do it because the analysis tools will have those combinations built in there for you. But you can define your own load cases. So I'll say okay to that. We are ready to put on some boundary conditions, and to do that, what you do is you go to the boundary conditions now, since it's all geared up, and you can choose that, and you can say, do I want a fixed, a pinned, a roller, or some user combination of it? And this is actually, for my structural engineering house, I should let you guide me into this. Yeah, often I'll just put fixed connections everywhere, but that's really not a very good connection, because that's not accurate. Yeah, that would be every column comes down and has some incredible moment resistance, and when you do that, it puts all sorts of funny moment in the columns. Like, if you were going to put boundary conditions on this, what would you recommend? What's that? Pinned? Pinned is probably more accurate. Because pinned will be like nice, a bolted connection. It won't move in an XYZ, but it doesn't necessarily have a lot of resistance to bending. Going ahead and resisting bending, it involves kind of a special connection. So pinned is pretty good. I'll just put a connection at the bottom of these things. Now, if I put them all pinned, that means eventually I probably need to put some braces in here or something to resist the lateral. If you make them fixed, the good thing is, you know, it'll look like the structure won't collapse. You just sort of create a very hard connection to go ahead and make. But we should probably go through and put some braces in here or something like that to resist the lateral to keep the thing from flopping over. So if I want to do that, maybe I should put some braces in here. Let me say a structure. I'll go say some bracing. And I'll put some braces. Oh, well, let me do it in this view. 3D snapping. Nope. Let me go back to the main 3D model and do it over there. Some braces, a little bit of 3D snapping. Snap to you. It's always hard to find the middle of that one. Although if I was good, that's actually the boundary right there. Is it M for middle? There's actually a way, there's a whole snapping control language that I never use because I just don't use it often enough. That's just the end point of that one. I'm trying to find the midpoint of that. I want it to be 1, 2, 3, 1, 2, 3. Ooh, it's right about in, actually, I'm really, oh, there it is. Sadly, in my weird sense of perspective, I'm estimating it's way over there, and it's not even anywhere close. Okay, you're somewhere in here. I know you are, because I just found you. Actually, let me do this. I should do things the right way for you. Under Manage, somewhere in here, there's the ability to control what the snaps are. MEP settings, structural settings, panel, standards, parameters, units. Where is the snap settings? It's in here somewhere. Is it in there? Oh, is it under the options? So I tell you I never use these things, but I want you to know they exist, just so you can work with them. Tool Assistant.
It's under Manage.
Thank you. I thought it was. It's one of those things, again, you think you know, but you don't. And where is it hiding under Manage?
It's the magnet to the side of materials.
That little guy that I passed right over and ignored? That is incredibly obvious once you tell me that. Okay, so midpoints is SM. So if I'm over here and I say SM, typing that, I should be able to get more to the midpoints of objects. So that should help me in terms of, let me go back to the bracing. That's an endpoint, SM. That's actually the midpoint. It's interesting. I'm not even on the midpoint, but it's snapping to the midpoint. You see that? It's over there. Okay, so I got some braces going in this direction. I can put some braces in the other direction. Then put just a few braces in here, just so we have something, but we'll go ahead and even introduce, let it sort of fail a little bit. There's the midpoint there. There's the midpoint over there, or the endpoint there. Okay, so I got some braces. Not great, but you know. It's not going to completely fall now. Okay, we are ready now to go through, and we got boundary conditions. We got a little bit of bracing in there. We are ready to put some loads on this thing, and loads we talked about a little bit last time. Let's just kind of go through that. When you go through and put the loads on here, you can go to the Analyze tab and choose loadings right there. If you just want to start choosing some loads, the big choices are, again, point loads, line loads, or area loads, either placed manually or hosted. I always like hosted because that way the load will move if the object boundaries move. So it's a little bit safer that way. So what I'm going to do is I'm going to put a load on the floor by choosing the floor as opposed to explicitly choosing the area. So I'll say there's a live load. Oh, we get to go and choose loads. Loads all have a category. Right in here is where you can say which load case it is. So this is the dead load case. We should also put a live load on there. So for our dead load, you have an idea for like a concrete floor, how many pounds per square foot that is? With some steel underneath it? Any sense? Again, I don't know offhand, so you can guess.
75.
Okay.
How thick it is, I guess.
I'm going to say 100 pounds a square foot. Okay. Until you put that weight of all that water on top, then I'm going to make it worse. Although that I think would be considered a live load, but I'm not sure. Okay, so dead load minus 0.1 kips per square foot. I will apply that to, so let me get that floor. Oh, where am I? I'm underneath it. Oh, you know what it is? I'm so bad. Is that, no, it says structural. That's okay. It's making me think. I'm going to the area loads. Hosted area load. That should be okay. I should be able to come over here. Do I have to turn on the analytical model to enable it? Yep. That's what it considers the line of that. Next up, we're going to go ahead and put some live loads on here. So that, I did that very quickly. Let me warn you about that. Yeah, the analytical model has to be on in order to put the loads in there. If it's turned off right now, you can't just sort of put it on the elements themselves. Okay, so I will go to the Analyze tab again. I will say, let's grab another load. Again, we'll go through and put in some sort of a hosted, I think it's hanging over here. Loads. Loads. Hosted area load. We're going to create another load in here. This is going to be a live load. And we can give these names. Let me call this the occupants. And whatever we decide that is. If it's the 40 pounds a square foot occupants, if it's the 60 pounds a square foot occupants, is it the 80 pounds a square foot books, whatever it is that you're going to consider it to be here. We'll go ahead and put some loads in here and give them a name. So 40 would be 04. Okay, and with that in place, we can now go ahead and drop them on there. And we actually have two loads in there. Can you sort of see we actually have the orange load and the purple load? They're both, the orange load is really hard to see. Okay, we got two different loads. The color is an indication of different categories. But that's enough to get started. We're sort of okay in terms of getting going now. So let's stop and pause right there. I got some boundary conditions. I got some loads. We're probably in pretty good shape. Let me save that away. We'll call it loaded. Okay, and we're ready to go. So we're ready to analyze. As you're going to analyze, let me tell you about two big ways you might approach analyzing. It really depends on whether you want to do things in the cloud or whether you want to do things in a desktop tool. Either one of these things will work. Ultimately, it should give you very similar answers. It really ultimately depends on sort of what you want your interaction to be. Now, I don't think, we don't have the connector to eTabs loaded up right now, although we can get it loaded up so you can take this model to eTabs. If you're familiar with eTabs, analyze it there. Since I don't have that, I want to show you two other ways, two other tools. One's called Robot Structural, which is a free one you can download from the Autodesk site. And it, again, it gives you many of the same things. When I open it, it'll look very familiar to most of you because it's kind of like eTabs. Although my corporate sponsor shouldn't hear me say that, but it looks an awful lot like eTabs. Most of them have very, very similar functionality. The other one that I'll show you is just actually using the cloud to do it. Let me do the cloud one first, and we'll get that one kicked off just so you sort of see that, because that's a real easy one. So under Analyze, in your version of Revit, you could have this series of structural extensions that say Analyze in the cloud or send it over to Robot Structural. Let me talk about that because you probably don't have that by default, and let's talk about how you do get that. If you want to get that, what you need to do is go to, there's something called appexchange.autodesk.com, and basically download the extension. And the extension that we're going to download is just called Structural Analysis Toolkit 2014. And what is that? That is basically just, it is the series of little extensions that build this functionality right into Revit. So for any of the different analysis tools, we want to take it over to eTabs, we can take it over using their tool. If I need to take it over to like Robot Structural, we can take it using their tool. I'm going to go to Structural Design and sort of see what else is in here. That's Structural Design. Let me try Simulation and Analysis. All sorts of stuff out there. I'm just seeing if the eTabs connector is actually out here. Ooh, CSI Safe Converter. CSI Safe, if you like that. Yuzu. I don't know about that one. I don't know CSI Safe. Aurora. These are the companies that did them. I'm thinking about really where that is or whether we have to get it directly from the CSI people for getting it to eTabs. But there's different connectors, and you download those connectors, and when you download those connectors and put them in your version of Revit, you end up typically with these extra little choices over here. So it's in the same way, the eTabs connector would show up there too. So the Revit connectors include one that says Analyze in the cloud. Let's talk about that. That's actually the easiest thing you can probably do. If you say Analyze in the cloud, you get something that looks like this. It's going to go ahead and start to just see if you're connected to the cloud. So you need to be logged in using your Autodesk ID, the same thing you do for cloud rendering or downloading software. It's going to check out your model. It's going to upload your model. What it's really going to do is it's going to take kind of a simplified version of the model, just that analytical model, and pop it up there. And we're going to say, great, this is my CE 120B class. I have different types of reports, simple. We have different degrees of analysis. I'm going to go ahead and say do a fine grained analysis. Give me a little bit more to work with. You get to say that really for the self-weight, where you want to include that. It'll actually sort of figure out for you the self-weight of the structural elements. So, and include those. So if you already have that, or you don't necessarily need to include it if you use this engine, because it'll go through and compute that for you. We'll say start the analysis. And it's going to go ahead and cook away in the background there. Give us a report in a few minutes. Okay. The report that it actually gives you back, just so you know what it actually looks like, is something like this. When it gets back, this is one I ran before class. The simple frame, this is kind of a simple one. Let's kind of just take a look at what it looks like in terms of the report. You can view the model just to make sure that it looks okay, and that's kind of okay. It's just basically in the web browser kind of looking at the structural model as it is. We can go through and turn on things. Oh, for example, do you want to see the loads? Do you want to see the different load cases? It'll just sort of present information graphically in terms of what's going on there. But let me go back out here. What you can do is, let's go back over here and take a look at the report. And the report that it'll give you looks like this. It's a simple version of the report. Let me see if I can open this up for you. It's just a PDF version of a report. So it'll basically just give you a pretty high-level summary of basically what's going on in terms of how the mesh got broken up. Tells you about the different load cases. Kind of talks about the reactions for each of the different load cases at each of the different columns. It talks about the nodes, the displacements at each of the different nodes. A lot of the same reporting that you get out of a tool where it's actually happening on your local program. Just for all the different columns, really what the extreme loads are in terms of the maximum and the min, in terms of just the load there. Also, just in terms of all the bars, really, what is the max and min force, I guess in all the beams. Also for the slabs, it starts doing all that sort of analysis that kind of shows you just really what the stresses are in the slab for different load cases. Okay. And just a lot of stuff you typically get kind of in an analysis program. So, for people who just want kind of the answers but don't want to go through much work to kind of configure it all, a lot of information is kind of included in that. And this is actually what I'll call the kind of quick version of the report. Right now it's going through and doing another one for us where it's computing, just what is it, the kind of a more detailed version. I'm going to close that up. That's interesting. That's the Windows reader. I'm not used to that thing. Okay. Go back over here. The other way to do this that may be more familiar to you as you're working is to actually take it to a structural analysis tool. And let me show you what that looks like. So we can take this model. Oh, looks like that one just got done. I'm just sort of curious about what's included in the detailed report as opposed to the basic report. So pardon me for the brief paused interruption here. Completed with warnings. Structural view, those all look pretty similar. It looks pretty good there. Hang on. Data analysis. Go back to my dashboard. Completed right now. Oh, it says simple report again. I don't think I actually changed what I wanted it to. Oh well, not to worry. No, don't worry about that right now. Okay, let's show you the other way in terms of taking it to the analysis tool. So if you want to take it to the analysis tool, I'm hanging out over here in Revit. What I can do is instead choose like robot structural analysis, and when you do, you get the choice of either just doing the reinforcement check or actually sending it over. And what happens when you send it on over, you can have it send the model, you can have it update the model, or bring the results back. So what happens here is you actually have this option of, we're going to send it over to robot structural or ETABS, if you want to go that way. Do your work over there, resize things as you need over in ETABS. After you make your decision in ETABS, basically bring it back over here to Revit and update the model in Revit so that it reflects what you decided over in ETABS. So you have this like circular workflow. That way, you as the designer and you as the engineer kind of work together without kind of walking all over each other's toes. So I'll say okay to that. What it's doing, it's kind of creating a little project and sending it across. It's exporting all the elements over here in a way that the same thing was happening up in the cloud. Just in the cloud, it happened for us kind of transparently in the background. The nice thing about working at it over here in this version, though, come on, you. Come back over here. Let me switch over and see if I can bring that up again. It's looking ever so dark there right now, so I gotta figure out what's going on. Hang on. Oh, it's still working. It's doing a little bringing things in for me. Come on, you. Don't fight me. I had a copy open in the background, and I think it's not happy with me about that. Let's try that again. Over here, robot structural. Come in this way. Let it do its thing. So again, creating a report, taking in all the elements, transferring the essential information about the size of all your elements, the geometry, and all those pin connections. Again, I'm not going to see the report. I'm just going to try and open it up in robot structural so we can see it. If I come over to robot structural now, there is that model. You can sort of see it's the same model because I see those braces kind of hanging out in the corner. It is basically ready to go now. At this point, we can start viewing different things. We can go through and turn on different things that we want to see. So in the display properties, we can say that, oh, for example, we want to see the section information. And it'll put that stuff in there. We can go through and put the bar restrictions in there. For example, the section names, if you like to see that. All the kind of standard things you'd expect to be able to do. You can also go through and show the loads, for example. So, for example, if you want to see the load values, load distribution regions. Actually, that's not showing you much. Yeah, in terms of what the loads are and stuff like that. So at this point, it's just kind of reporting the same information you see over in Revit. But let's go ahead and run something, because then it'll actually be a little more interesting. In terms of the analysis, really, like eTabs and many things, you can think of this as being just sort of a very good calculating tool. So if you say that, for example, you want to see some of the diagrams on the bars, I'm going to let it do the calculations. Okay. We have a lot of information now that is sort of available, and let's kind of take a look and see what we can figure out. So, for example, if we just go panning around in here, you can start to see basically how it, I'm not sure what I saw there, but it wasn't good. Okay, you can actually even start to see there's a little bit of dipping here in terms of the slabs between the beams and stuff like that. It's starting to show us a little bit about the deflection, but let's go ahead and look at some specific things that it can show. For example, diagrams for the bars. We can, for example, see, I'm always bad about the directions, like the bending moment in each of those different bars. So, for example, you can sort of see the areas where the bending moment is occurring right now. You sort of see where the highest values are and the lower values and all that kind of stuff. We can go through and show the shear forces if you want to in any of the different members in whatever direction you want to go through and show. But let's go ahead and kind of do it probably a little more systematically. It's probably the better way to do this is to go through and choose a bar and just choose its properties. Okay. And you can start to see in an individual bar really what's going on. So in terms of showing, for example, the values of the shear and bending moment, you can sort of get that across its length. That's really what the values are as you go through. You can also go through and get this. You can get the displacement. So really along the bar in different places really precisely what the displacement is. It's kind of all that stuff you're sort of familiar with. You also get this notion of really what they call the code check properties, and this is this idea of really, how good is it relative to the current steel code in terms of the size it needs to be. And it calculates an awful lot of different things, but at a high level there's this notion of what they think of as a ratio, and that the efficiency ratio is sort of a very high level way of looking at, how is that thing relative to how big it needs to be to meet the shear, the bending, and the displacement criteria. Okay. Anything less than 1 is good. Anything greater than 1 is not so good. So I can tell you right now that this beam at this size, the W12 by 26, is overloaded. Okay, and we can dig into really trying to figure out, what is the governing case, really what the deflection is, really what the problem is, and go through and kind of individually look at any individual beam, and that's kind of okay. Any beam, boom, you can go through and do that. But at a high level, what you may want to do is something like this. We can say we want to do some steel design. We'll look at all the different members, and let me just run some calculations, and I'm going to not, oops. Zeros do not determine the accurate. Oh, what's going on there? Let's go over there. At a high level, here's a summary of the overall structure, and you can start to see for all the different columns, for all the different beams right now, really how they're all doing relative to the ratio. So for example, beam 22, 23, 24, those are probably those little intermediate beams that are the joists. Okay, they're all fine, they're happy. These bigger beams, beam 20 and beam 21, they're undersized right now pretty significantly. So I start having a little bit of guidance about where I should be focusing my attention in terms of changing the size. So 2 ways of approaching that. We could go ahead to beam 20 and beam 21 and manually size them up and kind of based on our own sort of notion really figure that out. Although there actually is a way we can set this up so that it can go through, and if you give it a collection of beam sizes, it'll figure out what it considers to be the most efficient beam that would meet the criteria. Okay, and do a little recommended design for you to be verifying all the time, but at least going through and based on the criteria you specify, go through and change things. So just roughly, let's take a look at it. For example, beam 20 and beam 21 look like they're pretty undersized right now. How you can go through and fix that is, I won't save that right now. Oh, beam 20 and beam 21, I almost need to find them. Let me go back to the geometry. So in terms of all the beams, I can go back and find where beam 20 and 21 are. Looks like they're those big ones right down the center. That's not at all surprising in terms of what's going on. So right now, there are W12 by 26s. They have some other sizes loaded in here. I'm just going to choose a very big one. Oh, like a 16 by 40 or something like that. Okay, that's going to invalidate the calculations. That's okay. Same thing to this one. I'm going to change it to 16 by 40. Again, the calculators have been invalidated, so it's okay. Here's what's going on. Let's go back and run the steel design again. Calculations. Little complaint about something with a deflection. I need to take a look at that. But for 20 and 21, where are we now? Still looks like, no, it didn't pick up my size. Darn it, as they would say. I need to go through and figure out why did it not pick that up, because I swear I just changed that. Object properties. That's fine. It didn't pick it up in analysis. Apply. Something about my analysis, yada, yada, yada. It's not in there. Why is it not updating it? We'll figure out why it's not updating it, because it didn't go through and pick it up. See if we can pick it up that time. Yep. It's still there. Yep, it's still having a problem right there.
Do we have to do something in the analysis tab before we go to the...
It sounds like it, yeah, exactly in terms of that, but let me think about really, in terms of basically running the calculations, preparing the results. Let's try that. Actually, I'm used to thinking of it that way. But again, I don't work with this all the time. Calculations. Let's try that. I'll certainly take suggestions. Nope. It's still too small, but, oh, actually 21 picked up. That's okay, that's a little bit better. Yeah, got to figure out why the same thing for 20 we have to pick up. We're missing some specific little nuance there, but don't let that dissuade you in terms of what we're doing. We know we're a little bit better on 16 by 40. It needs to be much better in terms of what's going on. So next time, we'll figure out what that little hitch in terms of that last little thing we need to do to get it to accept our new value is, and show you how you can actually say, you know, I trust you. Why don't you go ahead and figure out what the most efficient size is? Like, and make a recommendation to me, as opposed to having to do this. So fine, you basically bring everything as best you can into code compliance and go from there. Beauty? Okay, let us stop there. I spent too much time playing around with green roofs and walls and stuff like that. Hopefully that was helpful, but we'll get to the last little bit of this, because this whole capability of really letting it go through and calculate things, and then kind of being updated back into the model, incredibly powerful as a workflow. So I definitely want to show you how that works properly. Okay, so let us adjourn for tonight, and come on back on Thursday. We'll finish this out and start talking about those ventilation systems.